Many scientists at the start of the story of quantum mechanics were very resistant to these new ideas, and they had very good reasons for resisting them. These ideas seemed to offer an explanation for observable phenomena, and there were no other good explanations. But they disagreed with the core ways we thought about the world. And as I said, it's important to understand that even many of the scientists involved really did not want the world to have to be described this way, including, for example, Max Planck. And Max Planck was initially very resistant to the ideas of quantum mechanics, even though he was the person who started it. Now, as the theory developed, as a good scientist, he eventually did come to accept it, but with great reluctance. And I expect we all know of many people who only believe what they want to believe, and there's possibly a moral lesson here. But the reluctance in the case of quantum mechanics to believing it is extremely understandable. The problem was not only that it struck at our whole way of thinking about the world. If this quantum theory was correct, it would mean we would have to completely rewrite physics. And any new scientific theory has got a very high hill to climb. It has to give exactly the same answers as the old theories, everywhere those old theories and previous models worked. And yet it also has to successfully describe the phenomena that we couldn't understand before. Now, the prior theories of mechanics, like Newton's laws, worked very well in a broad range of situations. Our models for light, similarly, were quite deep, and it achieved a remarkable unification of electricity and magnetism. Maxwell's equations from the 19th century are one of the major triumphs of 19th century physics. So how could we, in some sense, possibly throw away all these models, which also do work very well in certain domains and scales? How could we possibly come up with a new basis for all of these that was fundamentally different, but nonetheless gave the same answers everywhere they did? That requirement that any new quantum mechanical theory should also give results that correspond in these appropriate domains with the classical results is called the correspondence principle, by the way. Of course, it was also true, as we looked more deeply at these various phenomena in light and atoms, that there simply was no way we could explain them with our classical view. And those classical models would themselves lead to contradictions with observed reality. For example, as we discussed, when we would try to make a model of the atom with the electrons circling around some charged nucleus, like a satellite in orbit around the Earth, we meet major inconsistencies. Existing mechanics and electromagnetic theory, as I said, would predict that any such orbiting electron would constantly be emitting light. But atoms, for example, in their ground states, simply do not do that. The challenge for quantum mechanics was not an easy one. To resolve these problems of light and the structure of matter, we actually had to tear down much of our view of the way the world works, to a degree never seen since the introduction of natural philosophy and the modern scientific method in the Renaissance. Scientists were simply forced to construct a completely new set of principles for the physical world. These were, and still are in many cases, completely bizarre. And they are certainly very different from what our intuition, or what we might call our common sense, says that they should be. And many of these principles simply have no analogues in our normal view of reality. But we're forced to do this. If we do not do this, we actually cannot understand our world, and we will prevent the development of large areas of engineering that can create very powerful and useful technologies.